Okay, so for my last lecture today, I'm going to talk about the contact process or the SIS epidemic model. It will mainly speak about finite graphs, but I'll also say a bit about infinite graphs. So let's see how this works. So I'll start by introducing the contact process or SIS epidemic model on a graph. So G is going to be a finite connected graph. The model is going to be in discrete time. Each vertex can be in one of two states. It can be healthy or it can be infected. Okay, so we'll denote healthy by state 0 or infected which is state 1. And so the state at a vertex V, xv, can go from 0 to 1. So a healthy vertex can be infected at rate, which is some infection rate beta times the number of infected neighbors of V. Okay. So this notation means that W is a neighbor of V, it's an adjacent vertex. And then if that vertex is infected, it infects V at rate beta. And also vertices recover spontaneously. If you're infected, you become healthy again at rate 1. Or if you like, you can think of there being you can have independent rate 1 Poisson processes at each vertex and rate beta Poisson processes on each edge. Okay. And if your Poisson clock at a vertex sticks, and if the vertex is infected, it becomes healthy. If the Poisson clock on an edge sticks and one end of it is infected, the other end becomes infected. Okay, so that's the model. Yeah?
Poisson clock of changing back to 20. So would it start at when the node gets infected, or is it continuously going?
Okay, good question. So the two are exactly the same because of the memoryless property of the exponential. Okay, so that's the model. And if the graph is finite, then what happens to the configurations xt? So let's look at xt is xvt, v in v. You keep track of all the vertices. This is clearly a Markov process. On the state space 0, 1 to the V. Now what happens? So let's look at the all 0 state, which means everybody is healthy, in which case nobody can become infected after that. So the all 0 state is absorbing. Okay. And reachable from all other states. Which means that eventually xt is identically 0. You hit this all 0 state and you get absorbed there on finite graphs. Okay, so this seems like a boring Markov chain. So what's going to happen here that might be interesting? Okay, so let's ask, so how long does this take? And let's define tau, which is a function of G and this infection rate beta as the first time to hit this absorbing state. On finite graphs, we could start from the configuration where everybody is infected, let's say. And then we ask how long it takes until the chain becomes absorbed. That's the worst case. Yeah, there is monotonicity here. If you start with more vertices infected, then you will stay infected for longer. At every future time, you will have the same property that more vertices are infected. Exactly, that's what I'm going to come to here. Yeah, okay, so we are interested in this question on finite graphs, but let's start by asking what happens on certain infinite graphs. So what happens on ZD? So the infinite d-dimensional lattice. Here, let's say, start with just the origin infected. And everybody else healthy. So on a finite graph, the infection has to die out, but on an infinite graph, it could survive forever. It's possible. So does it happen? Does it survive forever, or is there some finite random time after which there's no more infection? Okay, so it turns out so there is some positive constant beta critical such that if beta is smaller than beta critical, infection dies out with probability 1. And if beta, okay, in fact, even if it's less than or equal to this, and if beta is bigger than beta critical, then infection survives forever with some probability which is strictly positive. What the probability is will depend on how much beta is bigger than the critical value, but it's strictly positive. Yeah, it depends on D. Yeah, the critical parameter depends on D. Okay. And I don't think it's explicitly known in any dimension. At critical also it dies out, yeah. Okay, and we'll talk about trees later, but for the moment, let's hold off on that. Something more complicated happens on trees. Okay, so this is what happens on infinite graphs. And it's reasonable to think that if you look at finite but very large graphs, maybe there's some you still see this infinite effect in some sense, and it turns out that that's true. And that was shown in papers by Durrett and Liu and Durrett and Schonmann. Okay, I don't remember dates, but it's mid-80s, I think. Okay, so what they did is look at a large box in ZD. Okay. Let's say with 10 nodes. And let's start with, let's say, all the nodes infected and look at tau. So tau n is the time for infection to die out. And what they showed was that this expected time for this, the expectation of tau n is of order log n. If beta is smaller than the critical value, and it grows exponentially like some power of n. If beta is above criticality. Okay. And the power depends on beta. Okay, so that's maybe too heavy notation. Let me just write n to the gamma here. And gamma is a function of beta. Yeah, I think so, but I don't remember. Yes. Yeah. Okay. So the reason that happens for this, it's for the first part, it's monotonicity. For the second part, you have some small probability of hitting the all one state starting from just one infected, which then multiplied by the exponential still remains exponential. For now, it's just the lattice. We take the lattice and restrict it to a box. So this is our graph. Okay. Okay, so this is what happens on the lattice, and the question is, we want to ask is, does something similar happen for arbitrary graph sequences? Or what can we say for more general graphs? Okay. So question is, what happens in general? Okay, and the way we are going to try and address this is by giving upper and lower bounds on this epidemic lifetime for arbitrary graphs and seeing for what sequences they might match up. Okay, tell me if it's not very visible here. So just a bit of notation. So from now we are going to, okay, I could have kept this. G is our finite connected graph. And A is going to be the adjacency matrix of G. So there's a 1 between in the ijth position if there's an edge between vertex I and vertex j, and 0 otherwise. So this is a symmetric positive matrix. So it's going to have real eigenvalues, and and we can order them. So let rho 1 bigger than rho 2 bigger or equal to rho n be the eigenvalues of A. Okay, so what can we say about the epidemic lifetime in terms of these eigenvalues? So the work I'm going to talk about is joint work I did with Laurent Massontie and Massontie-Towsley. So the first result I want to state is this theorem. So if beta times this largest eigenvalue of this matrix, of the adjacency matrix, if this is smaller than 1, then the epidemic dies out in logarithmic time. Then the mean lifetime is bounded by something very precise. It's 1 plus log n over this gap between your infection rate and your cure rate. These are the adjacency, not the Laplacian. Yeah, these are the adjacency eigenvalues. Not normalized, not normalized. Yeah, for a d-regular graph, it would be d, exactly. Yeah, initial, all 1 initial condition, let's say. Yeah. So, yeah. Okay, so the proof is going to be based on bounding this contact process by some other process called the branching random walk. So I'll introduce the branching random walk. There is a lower bound, but not similar. It's going to use the isoperimetric constant instead of this. No, under a stronger condition that something else is bigger than 1, we have a lower bound. Yeah. Okay, so we are going to bound xt by something called a branching random walk. Which I'll denote by yt. Okay, so how does this behave? I'll just describe it in words and not very formally. So for the contact process, every vertex is either infected or healthy. For the branching random walk, at every vertex you have some arbitrary number of infections. It may contain 0 infections, it might be healthy, it might carry 1 infection, or it might carry more than 1 infection. So at each vertex, there are YV infections, maybe there are 3 infections here. Okay, and then there are some neighboring nodes. Now, earlier there was a rate beta of this node infecting that node. Now, each of the infections here independently spreads at rate beta. So each of the infections here has children at neighboring nodes at rate beta. So that's the branching element. You have children at your neighbors at rate beta, and each of them also independently recovers at rate 1. So each infection will disappear at rate 1 independent of the others. And so you could have earlier, if this one already infected this vertex, this couldn't again infect it, but now they can both infect it. You just accumulate multiple infections at a site. Okay, it's not a very formal definition, but is the description clear? Yeah, exactly. Yeah. So the number of paths is growing like the largest eigenvalue to the k. So the number of potential infection trails is going like that to the power, beta times that to the power k. And if that process is supercritical, then then it survives forever. That's kind of died. Or rather here, if it's subcritical, it dies out very quickly. So if the branching random walk dies out, then your original epidemic also dies out. Exactly, yeah. Okay. Okay, so having loosely described this, I hope you'll believe me when I claim that we can couple the constructions of these Okay, so let's start them in the same initial condition. We'll start the branching random walk in the same initial condition as the epidemic, which is going to be the all one vector, and xt is going to be less than or equal to yt for all t positive. Okay. So if some site is infected, then it's going to carry one or more infections in the other model. Okay, so now let's look at the YT process, which is much easier to study, and let's ask what happens to the... Let's pick a vertex V and ask how many infections it carries at time t plus dt minus what it carries at t. So how does this change given everything you know about the Y process up to time t? Okay, so this expected change, well, each of the infections at at site V disappears at rate 1 independently. So you have minus IVT dt here, plus the sum over all its neighbors of beta YWT dt. Okay, because each infection from a neighboring site could give rise to an infection here at rate beta. Okay, so in vector notation, what we get is that the derivative of the expectation of yt is beta times the adjacency matrix minus the identity times the expectation of yt. Okay, and this is also my favorite type of differential equation. So linear differential equation, which we can solve. So Okay, and this was, the right-hand side was just the all one vector. Okay, so this is the great simplification we get by looking at the branching random walk rather than the contact process, that its expectation evolves according to a linear differential equation. Yeah.
The contribution from the neighbors
That's right. So the rest would have YW equals 0. Yeah, so that still works. Yeah. Okay, so now let's use this to bound the epidemic lifetime. Okay, so what's the probability that tau is bigger than t, that the epidemic hasn't died out by time t? So this is the probability that the x process at time t is not identically 0. The y process dominates the x process. Okay, or another way to say this is the probability, the number of infected sites at time t is at least 1. So this is the probability that if you take 1 transpose xt, this has to be bigger or equal to 1. There's at least one infected site if it's non-zero. And x is dominated by y, so this is the probability that it's more likely that the number of infections in y is at least 1. Okay, and by Markov's inequality, this is dominated by the expectation of this. Okay, and we already have a bound for that, so this is 1 transpose times this matrix e to the beta a minus identity t times 1. Okay, so this is a quadratic form by Rayleigh-Ritz. This is bounded by the inner product of these two vectors, which is n times the largest eigenvalue of this matrix. The eigenvalues of A are easily related to the eigenvalues of this quantity. So you get here e to the, okay, I'll write it as minus 1 minus beta rho 1 times t. And we assume this quantity was, beta rho 1 was smaller than 1, so this is decaying exponentially. So okay, and that's pretty much it. So to calculate the expectation, it's straightforward. Okay, so the expectation of tau is the integral naught to infinity of the probability tau bigger than t dt. Okay, and we can dominate this. So this probability is less than or equal to 1 if t is smaller than log n over 1 minus beta rho, and it's smaller than e to the minus t, or e to the minus t minus that. if t is bigger than that. Okay, and then you just do the calculations, you get this. Okay, so that proves this theorem that if your if this condition is satisfied, then the expected epidemic lifetime is logarithmic in the number of vertices. Okay, I should have said that a long time ago. N is the number of vertices. Okay, can we get some kind of matching or approximately matching lower bound? So for that, we look at the isoperimetric constant and a slight generalization of that, which is useful in applications. So the generalized isoperimetric constant we are going to introduce an extra parameter to define this, some number m, and it's going to be the minimum over all subsets S of vertex set of cardinality at most m of okay, so this is an edge isoperimetric constant. We count the number of edges crossing from S to its complement and divide by the size of S. Okay, so we have some graph. We pick an arbitrary subset of vertices. We count how many edges go outside. Okay, and some of them may go to the same thing. It doesn't matter. We count the number of edges and divide by the number of vertices. There's also something else which is called the vertex isoperimetric constant. That's not relevant to us. And usually the usual isoperimetric constant is usual isoperimetric constant is eta of n over 2. Okay. Usually you allow all subsets up to size n over 2. The reason we might restrict to something smaller is for some graphs you don't have good expansion all the way to n over 2. You might have it till epsilon n or square root n or something. So. Okay, and a second theorem says that if beta times this isoperimetric constant is bigger than 1, then the expected epidemic lifetime is bigger or equal to something exponential. It's okay, there's some constant here. There's this quantity bigger than 1 raised to the power m divided by m. Of the Laplacian, though, not of the. Yeah. M need not be n over 2. But if you want kind of interesting bounds, you want m to be at least some fractional power of n, let's say. Then you get lifetimes which are exponential in some fractional power of n. Okay, is the statement of the result clear, and kind of what kind of scale you want m to be to get something interesting? Yeah, in general, yes, it's a...
Yeah, you can do the...
Okay, that would be interesting to, yeah, discuss that. Yeah. Yeah, in general, it's hard to relate these. I'll discuss a few examples where it does and doesn't match. In general, you can't say if these are close. But if these were close, if eta m was close to rho 1, then you have something similar to a sharp threshold where you go from, for a small change in beta, you go from very short lifetimes to very long lifetimes. Okay, I won't go through the details of the proof, but the main idea here is again to couple this with something. So we look at the number of infected nodes, which is not a Markov process. So let Zt be the number of infected nodes at time t. Okay, let me call that nt. Let nt be the number of infected nodes at time t. And I'm going to define an auxiliary Markov process Zt. Zt is a Markov process on the state space 0, 1 up to m. Okay, and then this has transition rates so you go from k to k plus 1 at rate beta times eta m times k. And you go from k to k minus 1 at rate k. But from m, you can't go to m plus 1. That transition is blocked. Okay, what's the intuition for defining the rates this way? And I'm going to claim that nt dominates zt. We can couple them so that nt dominates zt. So if we are interested in the time for nt to hit 0, if zt hasn't hit 0, then neither has nt. Why did we pick the rates this way? Well, the contact process is evolving. At some time, let's say that k nodes are infected. It depends, to know what happens next, it depends which k nodes these are. But no matter which k nodes they are, there are at least this many edges going out from them towards healthy nodes. So new healthy nodes are getting infected at least at this rate, and the infected nodes are recovering at rate k. Therefore, it's reasonable that the number of infected nodes is growing at least as fast as the Z process. So we can couple NT and ZT such that NT bigger or equal to ZT for all T positive. And NT starts with all nodes being infected. ZT can only go up to M. And so let's start with Z0 equals M. Okay, so we have a random walk, a continuous time random walk, simple random walk, but with rates that depend on where you are. And it's a biased random walk where the rate of going up is always bigger than the rate of going down by some constant amount ratio. So if you start at M, you are going to see exponentially many visits, returns to M before you hit 0. And every time you are spending a residence time of at least 1 over M in that state before moving. So the total time spent here before hitting 0, the expected time, is the expected number of visits times 1 over m. It's bounded below by that, which is exactly the bound in the statement of the theorem. So we bound time for zt, for the biased random walk zt, to hit 0 from below. Yeah, so the drift is towards m, exactly, yeah. The drift is away from the origin, so you are attracted to the right boundary. Okay, some examples. Before I move on to examples, any questions? Yeah. I was going to come to them after the examples, but I hope there's enough time.
Also, going back to your first theorem, is it reasonable to expect that if I have, say, maximum degree B, three branching trees in the first case, or perhaps it might be
I don't know if it's the worst case, but yeah, I do get a bound on the, if you have a d-regular graph, then the eigenvalue is d, and that gives you a bound, but whether that's the worst case, I don't know. Okay. Yeah, so the first example, so let's look at G is the d-dimensional hypercube. So n is 2 to the d. Rho 1 equals d because G is d-regular. Okay, which means the all-one vector is an eigenvector of the adjacency matrix with eigenvalue d, and so that has to be the Perron eigenvalue because it's positive vector. And okay, you can work out eta m. So let's take m to be 2 to the k for some k smaller than d. Then eta m is d minus k. Okay, and so m is now, okay, so if k is alpha times d, then n is, then m is n to the alpha, and eta m is 1 minus alpha times d. Okay, so you can pick alpha to be some small constant, then eta m is close to d, rho 1 is d, so these two are close to each other, and you get this sharp transition from logarithmic to exponential in n to the alpha lifetimes. Okay. So you have a sharp transition here. So a second example is Erdos Renyi random graphs. If we are, Pn is going to be the edge probability, it will depend on n. If we are in a sparse regime, then there's a fairly big gap between these two things, but if we take Pn sufficiently large, So log n over n is the connectivity threshold, and if we take it growing faster than that, then the degrees concentrate around the mean value, NPN. Okay, and it's an easy fact that the spectral radius lies between the minimum and maximum degree. So if they concentrate, then it's equal to either of them. So the largest eigenvalue is asymptotic to NPN. And we can also show, if we take m to be some epsilon n, that eta m is also bigger than 1 minus epsilon n. So again, these two are close, and you again have a sharp transition. Okay, showing that is a bit of a messy calculation. You have to consider all subsets of various size. You get Chernoff bounds on how many edges go out of that subset, etc. Okay, and the same thing also happens for d-regular random graphs. Okay, so let's say dn regular random graphs. So rho 1 is always going to be dn. And if we take dn to be omega of 1, it's growing to infinity, then eta of 1 minus epsilon n is also going to be roughly as big as this. 1 minus, okay, or maybe there's a different delta than epsilon, but something, there's some other small, it's close to dn. So in all these cases, we get sharp thresholds. So let me give two examples where we don't have that. Okay, so with high probability, it's true that for your realization, they will have this property. Yeah, so there are two, there's randomness in the graph and then randomness in the process on that. But for most graphs, this is true. And similarly for the random regular graphs as well, there's randomness in both. Okay, the obvious counterexample where this doesn't work is the lattice. Okay. So that's in ZD. All these have good expansion. Yeah, yeah. So whereas this doesn't, so here your rho 1 is 2D because that's the number of neighbors. And eta m goes to 0 for, if you take any sequence n going to infinity, then those expansion goes to 0. So in this case, the bounds tell us nothing useful. Okay, you have one bound maybe, the upper bound tells you something useful, but the lower bound says nothing. So you need different techniques to show the threshold, which indeed Durrett et al. Did to show the existence of a sharp transition in ZD. And one more example is the star graph. Okay, so here rho 1 is square root of n is 1, eta is 1, because if you pick a leaf, there's exactly one edge coming out of that, or same for a subset of m leaves, m edges. And so there's a big gap here. You can analyze this system exactly. It turns out that if beta is smaller than any constant, any large constant times 1 over square root of n, then you have logarithmic lifetimes. And if beta is bigger than n to the minus half plus epsilon, for small epsilon, then the epidemic lifetime is exponential. Okay, so you do have a somewhat softer phase transition on the start, but there is a transition. And you can also look at these power law random graphs. It turns out that the dominant eigenvalues are determined by the highest degree stars of that graph. So you get indeed matching. The fact that these things match on the star tells you you also get similar transitions on the power law random graph. Okay, so that's all I wanted to say about the finite graphs, and I'm out of time, but I did say I'll talk about trees, and so I'll say a bit about what happens on trees. So let's start with infinite trees. So something very interesting was proved by, I think first by Liggett, and subsequently, okay, so let's look at regular trees. So every vertex has degree d plus 1. So let's look at d plus 1 regular trees. And start with, say, a specific node. You call that the root. You start an infection there. What happens to that infection? So does it survive forever? And it turns out that on trees, there are in fact two thresholds. So there exists so beta 1 and beta 2, such that if beta is smaller than beta 1, the epidemic dies out. If beta is bigger than beta 1, it survives globally or weakly. So what do we mean? To ask whether the epidemic survives globally, we are asking, if you look at large times, have you hit this all zero state? Has the epidemic completely died out? And it turns out that if you're above beta 1, that doesn't happen. The epidemic doesn't die out. But it dies out in any window around the origin. It could die out in any window around the origin, however big you are. Okay? So if beta is bigger than beta 2, it survives locally. Which means that the origin, and therefore every vertex, gets reinfected infinitely often. Okay, so for strong survival, a specific vertex gets reinfected infinitely often. For weak survival, any specific vertex only gets infected finitely many times, but the infection as a whole survives. And okay, the idea is there's a lot of space in a tree, it's growing very rapidly. So the epidemic might move off to infinity somewhere, but it still survives. And it was an open question for a long time whether these two, if beta 1 equals beta 2, or whether there's a strict inequality. And Leggett showed for d bigger or equal to 4 that it's strict, and I think Pimentel reduced it to d equals 3. And then Stacy gave an easier proof of both these, unifying them. They will depend on d. For d equals, no, I don't think, oh, good question. I don't know if there are exact expressions for this. Yeah. And then you can ask the same sort of question for branching random walks on trees rather than the contact process on trees. And there too, you can have, okay, so here there are always 2 transitions, but there you can have either 1 transition or 2 transitions. I don't know about regular trees, but it was also studied on Galton-Watson trees. And there it was shown by Pimentel and Tracy again that you can have either 1 or 2 transitions, and knowing something about the branching random walk doesn't tell you about the contact process. So the branching random walk can have 1 transition and the contact process can have 2. Okay, so those were some other things I didn't have time to tell you about, but was a very brief